Madame la vice-présidente, Monsieur le Président, chers collègues et amis, Mesdames et Messieurs, je voudrais remercier cordialement la Société chimique de France pour choisir notre travail pour le prix géographique Victor Grignard. C'est un grand honneur pour moi et une reconnaissance merveilleuse pour toute ma team. Je suis désolé même, je ne pas pouvoir présenter une conférence scientifique en français et je vais continuer en anglais. Alors, okay, so I think I better switch to English to continue to talk about the science and also talk about the connections with France to start off, because Mark already mentioned some of them. This is a picture that is certainly not complete, but highlights a few of our collaborations and contacts over the year. I will mention quite a few of them as I go through the science, but I would like now already particularly mention the group in Rennes and also Nathalie Tonjou at Montpellier, because I know that they have been working behind the scenes somehow to have this possibility to come today and to receive this award, and some of the others I will mention as we move along. But I would also like to mention that this is not a one-way connection, this is a two-way connection. Oh, I have to go to the microphone, otherwise you cannot hear me. I have to go to the it's clearly a two-way connection. In my team at Mülheim in the Max-Planck-Institute, there is the l'équipe tricolore that you see here. You may recognize the original ones behind the pictures. Alexis Bordet, I will talk in the second half of my presentation about his work. He comes from Toulouse, from Bruno Jodry's group, and joined my team. Christophe Verlet, who was in Strasbourg in his early education and is now an independent leader of a Max Planck research group, but we still collaborate a lot. And I will also mention some of his work. Nicole Keffer joined the team very recently, and so there will be, I will not be able to talk about his contributions today, but maybe later on. So what will I talk about? First, I give a very short introduction into the maybe somehow catchphrase power to X, to explain what we mean by this and explain the role of carbon dioxide and hydrogen in this realm. And then I'll focus on some C1 chemistry, so CO2 and CO, with a focus on manganese as the central element and why we've chosen manganese as one of our recent favorite element in coordination chemistry and coordination catalysis in this context. And as you will see, there's a lot about carbon here, but the critical element that we have to activate to get this going is hydrogen. And so this leads nicely into the second part, where I'll talk about some materials, not homogeneous catalysts anymore, but materials that are designed on a very molecular basis and have special features in the activation of hydrogen as we think. So let's get started. Let's get started with the problem and then try to find solutions. Our world today critically depends on the use of fossil resources, and in particular on petroleum. If you would take out all the things that have been made through the petrochemistry value chain from this room, or from your hotel room, or from your house, you will find that this will be a very empty and dull place very quickly. And we need a lot of it. We need the energy that is stored in the fossil resources, and we need the carbon that is stored. And at the moment, we're talking about around 100 million barrels of crude oil every day that is taken out of the ground. If you would fill this really in a barrel of 160 liter and put these barrels all next to each other, they go 1.5 times around the globe on the equator every day. So that is the sort of challenge that we're facing. If we think about a carbon neutral future, all this carbon has to stay in the ground, or it has to enter a circular economy and go into cycles as soon as possible. So this is a tremendous challenge around the world. But there is also tremendous opportunity here, because we start to see that we actually have the means to do this, because we can decarbonize the generation of electricity through wind, through through solar power, geothermal power, to carbon-free energy generation, electricity generation. We can take out the need of fossil fuels in this sector, and we see that there's a very great dynamic all around the world that makes this happening. And once we have that, we can combine these electricity sources, these energy sources, with renewable forms of carbon that are not coming from fossil resources, but they come from biomass, they come from recycled material, that's why I spoke about circular economy, and ultimately they might also come from carbon dioxide, which is either a waste of industrial processes, or comes from biomass generation, or from recycling, or ultimately even can be drawn out of the atmosphere. And then we can use this combination to make, for example, liquid fuels. And there are lots of projects around this, for this around the world. Just recently in the north of Germany, a plant has been opened to generate kerosene from CO2 and hydrogen to supply the aviation industry. It's still very small, but it shows where we can go. And also in the chemical sector, we can make a lot of useful chemicals out of these building blocks if we have the carbon-free electricity to keep that wheel going. So the decarbonization of the electricity sector enables the defossilization of the other sectors. That's the key message. And that was basically rephrasing power to X. So that's where chemical energy conversion comes in. But at the same time, of course, if you look at this in more chemical terms, we can see that we have to take CO2 through different oxidation stages. We start with CO2, which is the highest oxidized form of carbon, very unreactive, thermodynamically down in the sink, and then we add hydrogen as we move along, and with this we pump it up with energy, because hydrogen is the sort of very energetic, high energy molecule, and CO2 is the kind of very weak and tired molecule down here. So that is the chemical energy conversion. But chemistry means that at each of these levels, we have a lot of functional groups, a lot of molecules that ultimately make the products that we need. Be it solvents, be it textiles, be it nutritions, agrochemicals, and so on. So as chemists, we think in functional groups, and we see that they are at the same level of oxidation as the carbon here in the C1 compounds. And if we do this, we can make these chemicals in a better way than today. And that's the context of green chemistry. That's the heart of green chemistry, or le chimie verte, or chimie durable, sustainable chemistry. Green chemistry is the scientific basis of a sustainable chemical industry in a sustainable world. So that's the key in this message. So what we're interested in is finding catalysts that make these transformations possible, that make either the C1 compounds, or they take CO2 and hydrogen and make much more complex connectivities to form these ultimate products. And so this is a catalytic cycle for ruthenium on the hydrogenation of CO2, pulling it through to formic acid. That was the first level, still attached to the metal here. Then we add another hydrogen to go to the formaldehyde level, masked here as a diolate complex. Then we go one level up, another equivalent of hydrogen to come to the methanol level, and ultimately we split out methanol. And at each of these stages, we have the chemical possibility to connect more complex chemistry as seen before. And our research goes across the whole cycle, and not only the cycle on a molecular level, but also we reach from the molecular level to the systems level, to life cycle analysis in collaboration with my colleague André Bardo here, who is now at ETH Zurich, and we look at the overall systems performance. We design new chemical processes that are built on these reactions, and of course the mechanisms, the molecular mechanisms and the catalyst development is our core business here in this field. And what we see over many years is that, funny enough, the reaction with CO2 very often is very easy. It's very fast. The insertion of CO2 in a metal hydride bond is very often a very fast and relatively low energy pathway or step. But it's then the activation of hydrogen and the transfer of the hydrides to these intermediates to achieve the reduction, which is very hard. So it's not the CO2 activation very often that's the problem. It's much more often the activation of hydrogen to generate a hydride that's reactive enough to react with these intermediates to pull the CO2 along the pathway. And that's not so new to us. Actually, in a collaboration with Alain de Dieu in Strasbourg many years ago, it was proposed already at the time that the activation of hydrogen in this CO2 hydrogenation to formate, the last step, which proved to be rate limiting, was a hydrolytic cleavage of the hydrogen molecule, forming a metal hydride and a proton, and that way remove the formic acid. So this was an early example of a French connection for me to work together with Alain de Dieu at that time, which was a wonderful collaboration pointing that out. And we still see this today. This ruthenium triphos catalyst that was developed together with my colleague Jürgen Klankermeier, who shared the UCAMS prize with me for this contribution in Aachen, does it in a very similar way. It also does this hydride proton formation, this hydrolytic cleavage of hydrogen. It just has a hydride that is so active that it can even be transferred to the formate when it is bound to the metal, and that way moves CO2 beyond the formate level all the way to methanol. And that's still the only framework that can do this directly within the metal cycle. I will show you some other ways to get around this problem. And then our attention was drawn to manganese, because if one has a ligand attached to manganese, that is what David Milstein calls a non-innocent ligand. He introduced that concept that the ligands participate with the metal in the cleavage of hydrogen, for example. He pioneered this work. And manganese is very good at doing that. If you have a nitrogen here attached to the manganese in such a tridentate pincer-type ligand, which is called, for better word, macho ligand, and this framework PNP we use a lot these days. It's known for quite some time in the literature. This does exactly the same thing. It generates a metal hydride and a proton, and Milstein and Bella have shown very early on that you can do hydrogenations with these kind of catalysts about 5 years ago. Now, why is manganese so interesting? Well, there are two reasons. One is practical. If you compare manganese to ruthenium, you see that, well, there's certainly much more manganese around than ruthenium, and certainly at much lower costs, and it's economically and ecologically much more viable. Second, manganese is the metal that is in the center of photosynthesis. So it's used also by nature to do exactly what we're trying to do here, to activate hydrogen and CO2. And then in a very simple chemical term, I don't know, we used to be taught inorganic chemistry in the Hollemann-Wieberg book. I don't know whether you use the same in France. It's a classical German textbook. And Hollemann-Wieberg speaks about the diagonal relationship of metal ions. So, for example, a magnesium 2+ is more similar to lithium plus than it is to sodium plus or something like that. There's always kind of this diagonal relationship. And ruthenium 2+ and manganese 1+ are exactly also in that diagonal relationship. And they have the same electron configuration and so on and so forth. This is highly oversimplified. Of course, today we think about orbitals and all the rest of it, but this kind of simple picture in the Mendeleev periodic table, you have an ion here, N+ and N-1+ in the diagonal relationship. They could behave similar. And that extremely simple picture has proven tremendously valuable for us. But there is early work from France that I would like to mention here. Christophe Dassel and Jean-Baptiste Turtet in Rennes published some manganese catalysis very early on. And Guy Lavigne, who passed away untimely not so long ago, he was the first, one of the first to invite me to a lecture tour in France many years ago. And there is also this excellent review article here from his laboratory and his colleagues that I would like to point out here. So within a very short period of time, we started to get into this around 2017. Then a very short period of time, we found a lot of interesting chemistry, and that's just from our laboratories. And many other laboratories, the Bella Group, the Red Kempe Group, Luca Gonsalvi, Prakash, many other people in the world now look into manganese catalysis, and there's a lot of interesting chemistry coming out every day. And Christophe Verlet, my colleague, just published a very nice review article on reductive processes selective reductions with manganese. So I will only focus on the C1 chemistry, on the relationship to CO2. And it took us a long time to find a manganese catalytic system that finally hydrogenates CO2 all the way to methanol. And you see the turnover numbers here are still very modest. But for a 3D metal, they are among the highest that are known. There are only there's only cobalt as the other system, 3D metal, that can do that. So we're quite happy about this. But there was a lot of challenges to overcome. Because the direct hydrogenation doesn't work, it's only ruthenium that can do that. But there is a concept that one goes through methyl formate as the intermediate and hydrogenates methyl formate. That was introduced, that concept, by David Milstein many years ago. And if you do this stepwise, it works very well. You can make with a manganese catalyst methyl formate, and if you take methyl formate and hydrogen, the manganese catalyst will do the hydrogenation. But if you do it all together, it doesn't work. There is no way, and the reason is because CO2 is in the atmosphere. And as I pointed out earlier, CO2 inserts in the metal hydride bond very easily, but then the metal formate complex is like a dead end. It's very energy, it's the sink in the catalytic cycle, also shown by DFT calculations, and it does not turn over this step anymore. So what we were searching for and systematically trying to find out, and did a lot of tests and variations to take something that picks up, that is more oxophilic than the manganese, picks up the carboxylate and replaces it with something that is more weakly bound to this manganese nitrogen center and releases the catalytic active center again. And titanium tetraisoproxide was finally found to do a good job here. It does that, it picks up the formate, actually it even catalyzes the transesterification to make the methyl formate, and that's now the limiting factor. So the manganese is perfectly fine doing this reaction, but we need something to kind of wake up that sleeping giant here, this particular complex. Now, if we see that, what we can, of course, think is, well, why don't we avoid that intermediate and find a way how we can avoid that formate step altogether? And the way to do that is to go from CO2 to CO, to carbon monoxide, because then the formate complex is eliminated. And again, Bella and Prakash have studied this with either ruthenium or manganese, mainly again in two-step processes here, and they used amines to form the formamide intermediates. But of course, that's not so nice, because then you have the amine as additional component, you start to have difficulties to separate everything from each other, methanol starts to alkylate the amine, but it was a very conceptually interesting step forward. Now, we thought that it's much easier to take an alcohol to activate the carbon monoxide, because alcohols and CO, in the presence of base, give actually formate esters. And if you use methanol as the alcohol, we have nothing else in the reactive system than the product, the gases, and the catalyst. The toluene here is just used on a laboratory scale for some analysis, but in reality, we don't necessarily need it. We can run the reaction in methanol. And this is now what is called a liquid phase methanol production process. This is not completely unusual. Heterogeneous catalysis has studied that. There was a large test facility in Kingsport, Tennessee, 300 tons per day, so that's a real big plant, making methanol in the liquid phase with a heterogeneous catalyst, with a classical methanol heterogeneous catalyst. And now manganese is doing the same, and you see we're getting into some turnover numbers that are much more reasonable, and we understand the catalytic cycle. It's this manganese hydrogen activation that is crucial here. The CO is picked up by the base to make the formate ester, and then the CO bond is hydrogenated and off it goes. And we really use this very simple picture now for the design of catalytic cycles. It may be oversimplified, there is more subtleties to it for sure, but this simple picture to have that step and then a polar bond that picks up the two hydrogens, or vice versa, delivers the two hydrogens, the proton and the hydride, in a dehydrogenation, opens a whole manifold of catalytic reactions that we can look at. So we can either hydrogenate or dehydrogenate at the same manganese nitrogen center over and over and over again. And if that's true, the reverse reaction should also work. So we start from methanol, and we decompose it to CO and hydrogen. There is a lot of interest in methanol as an energy carrier, where people would do methanol reforming, reacting methanol with water to form CO2 and hydrogen to get the hydrogen out. We think that decomposing it to CO in the chemistry world is maybe even more interesting because CO is used everywhere, and we can use the carbon monoxide back out of that again. And that reaction works very well. Now, this is the only example that I will show you where ruthenium has beaten manganese in the first screening, and so we focused on ruthenium. Some of the other reactions, like the one I've just shown you previously, actually manganese even beats the ruthenium in the same ligand framework. So this is what we do. We decompose methanol in a closed reactor. There is significant pressure raise, so you get syngas under up to 12 bar pressures out of this reaction. And the reaction stops because it reaches equilibrium, and there is exactly the 2-to-1 ratio of the stoichiometry that you would expect here at the end. Interestingly, this kinetic profile has two very distinct regimes. There is a very fast regime that produces mainly hydrogen, almost pure hydrogen in the beginning, and then the CO formation comes up and catches up in the second phase. So there are two distinct elementary steps involved here, as proven by the deuterium isotope effect, which is about 1.3, 1.4 for the hydrogen evolution, so relatively small, but it's about 7, very large, in the CO formation. So there must be two distinct elementary steps involved in here. And if you look at the very complicated catalytic cycle, you will see that it's actually very simple. It's again this hydrogen activation step, and then we can separate these cycles into one that is only, the upper half is only forming hydrogen, and in all these steps, the CH activation occurs at a sp3 carbon-hydrogen bond, which explains the relatively low deuterium effect, whereas the lower half here, that's the CO formation steps, and in all these steps there is an sp2 CH bond activation at the metal center, which is in line with a much higher deuterium isotope effect. So even though, again, this is just a sketch, it's not a mechanistic study in a way that we've proven all the elementary steps, it's in line with all the experimental facts that we have. Now, if we can form formaldehyde in all these reactions as a possible intermediate, it's too unstable. It either reacts to the formate back, or it is hydrogenated quickly to the methanol. We cannot trap easily the formaldehyde, which is strange because nature in the photosynthesis uses CO2 and water to make carbohydrates, which is exactly the formaldehyde level. So what we thought was, isn't it possible to capture the formaldehyde on the fly as it is formed and do some interesting reactions with it? And one very interesting reaction that of course an aldehyde can do is aldol condensation, because then you form a carbon-carbon bond. So our aim was to generate formaldehyde and at the same time dehydrogenate the alcohol that was used to activate the carbon monoxide in the formate ester. And then the two carbonyl compounds would undergo CC bond formation, and in the presence of hydrogen, they are rehydrogenated to give the saturated methylated alcohol. That looks like a very daring thing to do. In fact, it isn't, because it follows the so-called borrowing hydrogen concept of Jonathan Williams. And there are many examples where you mix two alcohols and they do the same thing. But the trick here was to actually generate formaldehyde from these reactions that we studied before, and it works extremely well, and actually surprisingly well. And it's a completely new reaction for syngas. It's a new synthetic process that uses synthesis gas to methylate alcohols in the beta position, and you see the yields are really fantastic. And in this reaction, again, the manganese macho works significantly better than the ruthenium in the same ligand framework. If you would tune the ligand, you might change that ratio. And I don't want to spend any time on that, just to show that this is not a singularity. This reaction works for many, many alcohols, some biologically active systems here, even functionalized alcohols can be tolerated. It goes for aromatic, non-aromatic. You can alkylate ethanol up to butanol or propanol, and so on and so forth. So it tolerates double bonds, so you can do that reaction in the presence of a double bond, and it works very nicely. You have to do it under high pressure with synthesis gas, If you prefer to do this just in the liquid phase, you start from methanol and you enter the formaldehyde from the other direction, not from Cu, but from methanol, and it also works very nicely. And that is just one application case. This compound is called methyl propanediol. It's a technical product which is made today from propene in a very messy way. And if we now do this by methylation of propanediol, which can come from biomass, I think that's a beautiful example for green chemistry, where you see that the petrochemical value chain not only is based on the fossil resource, but also has a lot of problems otherwise ecologically associated with it, and is a multi-step, high-energy process that generates lots of waste, and that is a very clean alternative to get this useful product. So in summary, well, is manganese the better ruthenium? Maybe not yet. Still, there is, of course, much more ruthenium chemistry out there, and ruthenium has some outstanding catalytic activities. But don't forget, this is done for almost 60 years now, ruthenium catalysis with Jeffrey Wilkinson starting it in the 60s, and manganese were probably 6 years down the road. So I think there is great prospect for manganese in homogeneous catalysis, and we continue to use that simple analogy to look for new catalysts. Now for the remaining time, I'll change gear completely in terms of the catalysts that we're using, but I still would like to take that picture of hydrogen activation, because that's what we saw is very critical to control the activation of hydrogen, either in a homolytic fashion or in an increasing polarized fashion, all the way to the heterolytic cleavage, to cleavage into H+ and H-. And if we think more broadly than the CO2 hydrogenation, this becomes very relevant if you look at such multifunctional compounds that have an aromatic group, another CC bond, and a very polarized CO bonds. And such entities are ubiquitous from biomass. So this is acetone and furfural, the condensation product. There are other furfural derivatives that come from biomass, HMF and others. There are also other aromatics that come from lignin, for example. So there's a direct connection to biomass utilization here, but there are also other petrochemical, very interesting reactions that follow that. And if you're interested, very recently we published an accounts of chemical research, Alexis Bourdais here, that I mentioned earlier, and there is the current state of this story summarized in this. And those of you who are familiar with the music of Pink Floyd, where I'm a great fan of, they might recognize that picture where the motivation was taken for that picture from the cover of Dark Side of the Moon. So how do we make these systems? Actually, we take a very molecular approach, and it's pretty simple. You use dihydroxylated silicon, and we didn't invent that. This is chemistry that's known a lot, and we silylate it with the TIOS concept. And there are two major factors that these molecular modifiers for the surface have to bring in. Firstly, they have to have some entity that will then help us to stabilize the nanoparticles, the catalytically active nanoparticles that we produce. So they have to have something in their backbone that is known to stabilize nanoparticles. And such imidazolium structures that are reminiscent of ionic liquids, they are very well known to do that. This is why this is then called a SILP material, even though there's no liquid phase on top of it, but these ionic liquid type structures are on there. So stabilizing nanoparticles. Second, we want to have the chance to introduce additional functionality. So they have to be easily modified, that we can introduce, for example, acid groups, basic groups, Lewis acid groups, and so on, because we want to combine the basic chemistry of the metal nanoparticle with the additional functionality of the support to generate multifunctional systems. And so this is done with the standard TIOS technique. Then we use organometallic precursors to decompose them into the nanoparticles. There's a lot of collaboration here with the group of Bruno Aujourd'hui, as I will show in a minute, and we can use all sort of precursors, even bimetallic systems, iron ruthenium, cobalt rhodium. We made a whole range of various systems, and then we get them after reduction, and we need to characterize them, and that's where we really need the collaboration within the Max-Planck Society and, for example, with the group of Bruno Aujourd'hui, because we come from a molecular background from coordination chemistry, so characterizing these materials with all sort of electron microscopy, X-ray absorption spectroscopy, and so on. We are critically dependent on the collaboration with my colleagues Serena de Beer, Robert Schlögel, other colleagues within the Max-Planck or with RWTH Aachen, and as I mentioned, a very nice collaboration with Bruno Chaudry in this area. So, we know what we have. For example, cobalt, rhodium on these supports and exactly their composition. They're all well behaved. The size is between, I would say, 1 and 4 nanometers typically, 1 and 5, not between 1 and 5 nanometers, very often around 3 nanometers, so very small, homogeneously dispersed particles. If they're bimetallic, they're fully alloy type, so it's possible to really make some well-behaved nanoparticles on these supports. And these are just some of the reactions that are summarized in this accounts article, so I won't go through many of them, just to highlight a few on the slide. There is the decarbonylation of a side chain in an aromatic ring, leaving the aromatic ring untouched. Very difficult to do. You could only do Clemenson or something like that. For hydrogenation, only less than a handful of systems can do that. These catalysts do it very well. Hydrogenation of fluorinated aromatics, leaving the carbon-fluorine bond intact. Again, only very few catalysts that do that effectively, and so on and so forth. So yeah, I'll just leave it at that and go to the last 5 minutes or so. That I'm not sure how I'm doing on time, but I think there's 10 minutes, perfect. So then I can spend a little more time on this last subject. Because what we've seen so far is that with this technique that I've shown you, if we have a reaction where we have a substrate that can undergo different products in the presence of hydrogen, what we will do is we will generate a designed catalyst to do exactly that transformation. So our method is very flexible. With the same technique, sticking on these ionic liquids and then making the bimetallic or monometallic nanoparticle and introducing the second functionality and everything, we can make a catalyst that is perfect to form product A, and with small variations, we make a catalyst that is able to make product B. So we're very flexible with our catalytic synthesis. Now, what would be nice if we would not be just flexible, but if we would be adaptive. So if we had a catalyst that makes product A, and then without making a new catalyst, in the same reactor, we just tell the catalyst, please make now product B. So we need something to switch the catalyst from stage A to stage B, some kind of a stimulus to say, hey, well, you've made product A, great, but now for the next 2 days, please make product B. And then we switch back to make product A. And even the catalyst ultimately might even recognize by itself that we don't have to tell him, but he might recognize that it's now time to make the other product. So we need a switch here, a stimulus that is fully reversible and very fast to do this almost in real time. Now, we joined up with Philip Jessup in Canada because Phil has developed so-called CO2 responsive materials. That was a great contribution. He actually was awarded the Enichem award some years ago for this. And he made these polymers, which are called PGS polymers, that have an amine functionality at the end. And if they see CO2 and a little bit of water, they form carbonates, bicarbonates. And so they change from non-polar to very polar in the presence of CO2. And he developed a whole range of nice chemistry about that. So we thought, well, we can do the same. We just take his PGS stuff, put it on the silica surface, then generate a ruthenium catalyst. And that ruthenium catalyst should be in a different environment. If there is no CO2 present, if it only sees hydrogen, that's what it sees. If there is CO2 present, some change will happen, and maybe that gives us this stimulus to do it. So, does it work? Well, I guess you already figured that I wouldn't tell you if it wouldn't work, so here is the example. This is furfuryl acetone. In the hydrogenation, there are all these possible intermediates, and these are the two hydrogenation products at the end where the aromatic is hydrogenated, and then it can have a ketone here or an alcohol function here. And if you take normal ruthenium on silica, it's an excellent hydrogenation catalyst, and it always, whatever you do, it goes through the deep hydrogenation to hydrogenate the aromatic ring, the CC double bond, the CO double bond to form this alcohol. That's known, and that's what we expect. And the ruthenium doesn't care whether it's hydrogen or hydrogen and CO2. It does the same, it just ignores the CO2. The ruthenium on the same support, now with the PGS molecular modifier, changes completely when CO2 is present. If no CO2 is present, it does the same as before. If CO2 is present, it shuts down the last hydrogenation step and makes very selectively the hydrogenated ketone. And that is not just like under the optimized conditions, it's really, you see the kinetic effect. This is the kinetics in the presence of hydrogen. Very quickly the CC double bond is hydrogenated, then it forms the ketone, and then very fast the CO hydrogenation is the last step. In the presence of CO2, the CO hydrogenation is basically shut down completely. The other steps are similarly fast, not quite as fast, a little bit slower, but the main point is that the ketone hydrogenation is completely shut off. So we were very excited and we thought, okay, yes, that's because it forms these carbonates, but the story turns out to be a little bit more complex. And when we did all the analysis of the material, what happens in the presence of CO2 and hydrogen, actually we came back to a reaction that I spent the first 30 minutes to tell you about. It's the hydrogenation of CO2 to formate. So on this support, on this basic support, CO2 and hydrogen react to give an ammonium formate layer. And that seems to be responsible for the selectivity switch. It's that catalytic activity of ruthenium to hydrogenate CO2 and form formate species on the surface that kind of blocks certain active sites that the ketone hydrogenation is completely shut off with these systems. And that is fully reversible. We have the full analytics for that, and it is fully reversible, and the reaction is reversible very fast, luckily for us. So we can do this in a continuous flow reactor. There is the catalyst bed inside here of this reactor. This is the ruthenium on the surface. CO2 is switched off. Only substrate and hydrogen pass to the reactor. We get the ketone. Then we switch on the CO2 into the gas stream. Nothing else. That's all we do. We just switch on CO2 in the gas stream. The formate is formed, and immediately the selectivity switches, and out of the reactor now comes the ketone. And we switch it back. And we switch it on and off again, and we can do that as often as we want. And very quickly, almost in real time, the selectivity switches. So the catalyst adapts itself to the presence of CO2 or not, which could be also interesting for hydrogen sources, because some hydrogen sources, there's pure hydrogen, some renewable hydrogen sources have CO2 in there, so the catalyst would recognize what type of hydrogen mixture it sees. So this is, again, not only furfuryl acetone, but all kind of unsaturated furfuryls show the same selectivity. There are other functional groups now. This is unpublished work just going on. We've now extended that to other functional groups that show similar selectivity switches in the presence of CO2. So it seems to be more general than just this one substrate, and more general just than even the substrate class, to be able to use CO2 on these supports as a very fast switch. So we can use CO2 as the stimulus here to make the catalysts adaptive along this way. So with this, I would like to conclude. I hope I've been able to show you with two rather different approaches that using hydrogen that comes from renewable sources together with renewable carbon sources, CO2 and biomass, opens the possibility to develop green chemistry pathways to, on a very large scale, it could be fuels, and in particular also in the chemistry value chain. And together with Paul Onassis and Julie Zimmerman, we wrote a little science piece about this concept, where green chemistry is going, and basically that this idea of circular carbon is a centerpiece of the future developments. And with this, I would like to thank in particular my team. That's the team at the Max-Planck-Institute for Chemical Energy Conversion. Just before we went into lockdown phase, you see they're all wearing the t-shirts that say always use the green chemistry tools here. I photoshopped in Nicolas Käfer because he wasn't around at the time. There is again Alexei and Christoph, I mentioned their work. Andreas Vorholt, who does all the reaction engineering work in our team in Mülheim. I haven't had the chance to speak a lot about his multi-phase approaches, but for example, this reactor design that I showed you, his team is very incremental. Markus Hölscher does a lot of the calculations with us. He's at RWTH Aachen University. So is Giancarlo Francio, who is also very active in the multi-phase catalysis, and actually also in asymmetric catalysis. We still have an interest in making chiral molecules and doing asymmetric catalysis. And Giancarlo is also leading a Beethoven project together with the University of Poznań that we will hear in the second talk today, some research from there. And Niels Thijssen, he's the head of the technical laboratory at the Max-Planck-Institute for Kohlenforschung. We have a very close collaboration, a so-called joint workspace together with them. With this, I'm at the end, and I would just leave you with kind of two quotes. Of course, I have to quote Max Planck, as I'm now working for the Max Planck Society, and I'm happy to do so, because he's assigned this motto of the Max Planck Society: insight must precede application. So we're very much application-oriented. We want to see our things happening in reality, and we have some CO2 chemistry that is finding its way into industrial reality, hopefully. At least it's tested at a large scale. And so that's great, but we want to do this from a very fundamental standpoint and starting from very fundamental ideas, as you have seen, even though they're very simple, but they're very fundamental. But an even more true quote probably from Nelson Mandela: it always seems impossible until it's actually done. So I hope to leave you with a kind of an optimistic message on the future of chemistry and the future of our energy systems and the connection between energy and chemistry. It seems impossible, but I'm sure we will do it. Thank you very much indeed.